Now that students are familiar with bonding and antibonding orbitals, it's time to start molecular orbital theory for diatomic molecules. Diatomic molecules are composed of two atoms, and as usual, we'll start with the simplest example and build on that with bonding in the hydrogen molecule. The hydrogen atom has one electron in its 1s orbital, and that orbital is shaped like a sphere. We'll represent the energy of the electron in this orbital with a line and the arrow for our electron. So there is one hydrogen atom on the left and one hydrogen atom on the right. These are the atomic orbitals. Addition of the orbitals in the same phase results in energy stabilization. Remember way back when the energy of the orbitals could be represented by minus quantity z squared hr divided by n squared. So adding two negative values together produces a larger negative. That is why the energy decreases. This would be a sigma orbital. So this is a bonding molecular orbital. It's lower in energy than the two incoming atomic orbitals, and it stabilizes the molecule and results in a bonding interaction. If one adds the two atomic orbitals with opposite phase, red and blue don't mix, so we get an antibonding molecular orbital. This would be a sigma star orbital. Notice it has a nodal plane between the two atomic nuclei, and the energy of this mixed orbital is higher than the two incoming atomic orbitals. So we call this an antibonding molecular orbital because it's at higher energy than the atomic orbital, and this would destabilize the formation of the molecule, making it less likely to form a bond. Now we need to place our electrons, and according to electron placement rules, each electron will go to the lowest energy orbital available, which is the bonding MO. Notice we've had conservation of orbitals. Two atomic orbitals went into the mixture, and two molecular orbitals came out. So when getting the bond order using molecular orbital theory, one uses the formula electrons in the bonding MO minus electrons in antibonding MOs divided by 2. Another way to put this is no star electrons minus the star electrons divided by 2. In my mind, I've named this the Sneetch rule. Remember the Sneetches on the beaches with stars upon thars? So if we look at the electrons in the bonding orbital, we have 2 of them. And if we look at the electrons in the antibonding orbital, there are none. So doing the math, 2 minus 0 divided by 2 gives us a bond order of 1. And isn't that what one would expect for the hydrogen molecule? MO theory has predictions to make about the formation of other molecules. For example, let's consider bonding in helium-2. Helium is a noble gas, so it's unlikely to bond, and MO theory confirms this. If we look, this time we have the same molecular orbitals, but instead of one electron coming in from hydrogen, we have 2 electrons coming in from helium, which means a total of 4 electrons in the diagram. So when we place 2 electrons in a bonding interaction and 2 electrons in an antibonding interaction, the diagram shows that we have done something to stabilize and form a bond, but also something to destabilize and break a bond. Those 2 forces are equal. So if one considers the electrons in the bonding MO, there are 2. The electrons in the antibonding MO are also 2. 2 minus 2 divided by 2 gives us 0. This tells us that helium-2 is unlikely to form because it has a bond order of 0. There is nothing to be gained in getting the electrons to a lower energy orbital by forming this molecule. So now it's time to learn about that detailed diagram from the introduction. This is the general scheme for bonding of diatomics that have electrons within the second period. For example, things like nitrogen, oxygen, or fluorine. To simplify things, we're going to assume that we're using the same atom such that the 2s valence orbitals are at the same energy level and the 2p valence orbitals are at the same energy level. When dealing with two different atoms with different electronegativities, there will be slight distortions to this diagram. Let's tackle the s orbitals first. The 2s orbitals are like the 1s orbitals, except larger in size. So when we combine them in a constructive way, we get a sigma bond. And when we combine them in a destructive fashion, we get a sigma star antibonding orbital. We'll start with these two p orbitals that are oriented horizontally along the x-axis. When we combine them in a constructive manner, overlap occurs between the nuclei and we have a sigma orbital. When they are combined destructively with a different phase, then we get a nodal plane and a sigma star orbital. Now let's work with the p orbitals along the z-axis. So that would be this one here and this one here. If they are combined in a constructive manner, they're meeting sideways. So that means we're making a pi bonding orbital. And if they are combined in a destructive fashion, we get a pi star antibonding orbital with a vertical nodal plane. Now let's work with the py orbitals. These are coming out of the screen and going back into the screen. There's one on each side. Here's the one on the left side and the one on the right side. So once again, these p orbitals are meeting sideways. So we would get a pi bonding orbital when we had constructive interactions. So we have a lobe coming out of the screen and a lobe going back into the screen. And as you might guess, if there were destructive interactions, then we would get a pi star antibonding orbital with a vertical node. So notice that we have 4 atomic orbitals on the left side and 4 atomic orbitals on the right side. This should produce 8 molecular orbitals, and it does. 1, 2, 3, 4, 5, 6, 7, 8. So let's try filling in one of these orbitals with the oxygen molecule. Oxygen is in group 6. So we'll have an oxygen atom with 6 electrons on one side as an atomic orbital, and an oxygen atom on the right side with 6 electrons as an atomic orbital. Now it's time to put our electrons in the diagram. That will be 12 total electrons. So lowest energy first with opposite spin for the second one. 1, 2, 3, 4, 5, 6, 7, 8. Don't forget Hund's rule, which says when placing electrons in orbitals with the same energy, they must be spread out and pointed the same direction. So that was 7 and 8. Here is 9 and 10, and 11, and finally 12. What about the bond order? This would be bonding electrons minus antibonding. So when we look at bonding, we have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons in bonding MOs. What about antibonding? 1, 2, 3, 4. So 8 minus 4 divided by 2 gives us a bond order of 2. And that's what we would predict with a Lewis structure. But there's something different between MO theory and Lewis theory for drawing a molecule. The Lewis structure predicts that oxygen is diamagnetic. That means it does not interact with a magnetic field because it has no unpaired electrons. We either have shared pairs or lone pairs. On the other hand, MO theory predicts that oxygen is paramagnetic because we have two unpaired electrons in this pi star orbital. So this predicts that oxygen will interact with a magnetic field. Which one is right? In this video, we have two magnets. Here is liquid nitrogen being poured between the magnets. It doesn't stick. Here is liquid oxygen being poured between the two magnets. Notice that oxygen is attracted to the magnetic field. So it appears MO theory is correct and that oxygen has unpaired electrons. So how about those famous Star Trek dilithium crystals? That would be a diatomic molecule with two lithium atoms. Lithium has one valence electron in the second period. So when we place those in the MO diagram, we're going to wind up with two electrons in the bonding molecular orbital. So as you might imagine, this predicts a bond order of 1. So you can see that Star Trek was based on some real scientific principles. It would be hard to find two lithium atoms together without additional lithium atoms around them. A collection of lithium atoms does have a bonding diagram, but that comes in Chapter 8 when we discuss band theory. Here's your question. What is the bond order and how many unpaired electrons are in the cyanide ion? So let me help you get started. Carbon is group 4, nitrogen is group 5, and the charge on the ion is -1. So we need to add that as well. So that is 10 electrons to place. Please put your 10 electrons in this diagram, and you can tell visually if you have paired or unpaired electrons. And for bond order, don't forget no stars minus stars divided by 2. Here is a similar question of a different compound, this time more hypothetical. Get the valence electrons for nitrogen and fluorine and add them up, and then place them in the diagram. Then use your Sneetches on the Beaches formula.